Hello and welcome. So, today we will give you a brief overview of how a general Lie group is defined, and we will discuss the one of the main results in this theory, which is the Lie group Lie algebra correspondence. Now, to understand Lie groups, one needs to have background on the so-called smooth manifolds. So, I will begin by defining what is a smooth manifold, and then as soon as you define a smooth manifold, just like we have seen for subsets of Rn, smooth manifolds locally look like Rn. So, at every point you can draw tangent spaces and you can do kind of differential calculus, and this tangent varies smoothly over all points of a smooth manifold, so you can also vary the calculus smoothly. So that's roughly the idea. But there are technicalities in order to define that, and we will just give you the definition, and then we will give you the general definition of Lie groups and discuss basic properties. We are not going to give you much detail in this coming two lectures. We don't have this. I mean, giving the details is beyond of our aim or beyond our scope in this course. So we will start by giving you proper definition of a smooth manifold, and then I will define Lie group and then some basic properties, Lie algebra, Lie group correspondence, and then I will give you one example of a Lie group which is not a matrix Lie group. So for all the examples we have seen are matrix Lie groups, but not every Lie group is a matrix Lie group, and essentially that's my main aim, is to give you an example of a Lie group which is not a matrix Lie group. So that's the aim of this coming two lectures. So we begin by defining what is a smooth manifold. So let's see. Okay, so to define smooth manifold, we recall what is a topological manifold. So I will give you a detailed definition of a smooth manifold. At least that much you should take away from these two lectures, and then I will just give the statement of the group Lie algebra correspondence. So you start with a second countable Hausdorff topological space. Then M is called a topological manifold of dimension n if for each point P in M there is an open set U in M containing P such that U is homeomorphic. U is homeomorphic to Rn by some homeomorphism phi. Such a pair U phi is called a local coordinate chart on M. Okay, and you see you have phi x, then you can kind of you can have phi p, you have x1p, xnp. Okay, so the component functions are, so this x1 xn is a local coordinate. Local coordinate on U. Now example, all the matrix groups are topological manifolds. Okay, so Rn, Sn, okay, projective space, Pn, K, all matrix Lie groups. Okay, so all of them are topological manifolds. Now the definition. So now another definition. So let Mn be a n-dimensional topological manifold, a smooth atlas on M is a collection, okay, of charts by some indexing set of charts such that Ui is an open cover for M, and 2 this is called a smooth atlas. Okay, the second condition is kind of smooth atlas. The second condition is important. So for each pair of charts U phi and V psi in this set, the transition map psi compose phi inverse phi U intersection V to psi U intersection V is smooth. Okay, so essentially this is the picture. Suppose you have a set here, it is your some set, and you have a open cover U, this is V. You have an intersection here. Now here you have a kind of open set in, suppose this is a two-dimensional set, right? So something. So you have a open cover, it's called phi, Okay, and then you have another kind of coordinate chart, that is psi, and then what it is saying, that this intersection is mapped on the shaded region, and this map psi compose phi inverse is smooth. So this is smooth. Okay. So essentially this is the picture. This is U intersection B. The shaded region is U intersection B, and this is phi of U intersection B, and this shaded region is psi of U intersection B. So this is the picture, and smooth atlas means these transition maps are smooth. Okay. So now there can be several atlases for a smooth manifold. So two atlases on M are equivalent if their union is also an atlas. Now we are ready to define what is a smooth structure. A smooth structure on a topological manifold is an equivalence classes of atlases, and a smooth manifold is a topological manifold with a specified smooth structure. Okay, so the main point of introducing smooth atlases is to be able to differentiate the transition functions that appear here. So essentially we want to do differential calculus. So we are sort of covering the topological manifold by charts, and then on the intersection of two charts we should be able to differentiate the transition functions. And for this simple purpose, the particular choice of atlas is not important, because you start with a given atlas, you can always enlarge it and keep enlarging it until you get a maximal atlas, and you can get actually a unique smooth maximal atlas which gives you the smooth structure. Okay, so now let's see some examples of smooth manifolds. Examples of smooth manifolds. So of course Rn. Okay, so the atlas consisting Rn. So the atlas consisting of the identity map alone. Okay, so in general you take any finite dimensional vector space that has a smooth structure. Okay, so any finite dimensional vector space real vector space. Okay, real vector space has a canonical smooth structure. Okay, so one can take finite in dimensional. Okay, one can take the atlas consisting of all linear isomorphisms phi from P to Rn. Okay, the collection of all such map is an atlas. Since the transition maps are linear maps on Rn, and they will be smooth. And then now, yeah, so let M be an open subset of a vector space. Then the inclusion map is an atlas with one chart that provides the smooth structure. Okay, so now you see, so in particular, GLNR is a smooth manifold as it is an open subset of M and R, which is V in our case. Now, in this case, both GLNR cross GLNR to GLNR, AB goes to AB, and GLNR to GLNR, A goes to A inverse, are smooth maps. So smooth maps, how do you define? I mean, essentially you just use the smooth structure and you can define what are the smooth maps. Okay, so another non-trivial example, Sn is a smooth manifold and atlas is given by the stereographic projections. Okay, so the projective space is also a smooth manifold, and I don't give you the detail. Okay. Now, it may happen that on a space, on a topological manifold, there may be more than one smooth structure. So the smooth structure on a topological manifold is not unique. So another example. So real line with a single atlas x goes to x cube is a smooth manifold. Is a smooth manifold, and this atlas is not compatible with the standard smooth structure on R given by the identity map. Since the transition map I compose phi inverse y is y to the power 1/3 is not smooth 0. So in general, there may be many smooth structure on a topological manifold. Okay, and it is also possible to you take any set with no topology specified, you can make it to a smooth manifold. Okay, so but that smooth structure may be very different from the smooth structure that we have we want to have, like natural smooth structure on R. Okay, now what are the ways to construct smooth manifold? So here is a theorem, again without proof theorem, even though the proof is not actually difficult, but I would not give you the proof. So this theorem, it is a consequence of the inverse function theorem. So let f u to Rm be a smooth function on an open set U contained in Rn plus m. Choose C in Rm. Assume that for each A in F inverse C, dFA Rn plus m to Rm is surjective. Then F inverse C has the structure of an n-dimensional smooth manifold. Okay, so it is essentially it's the application of the inverse function theorem. I am not going to give you the proof, but I will give you one application of this result. Okay. So now, like we have done earlier, take F, define a map. So you remember what was symmetric N in the previous class we discussed? The subspace of n by n symmetric matrices, and it has dimension n into n plus 1 by 2. We discussed it in the previous class. Now define F(O)n to this by Fa is AA transpose. Then On is F inverse I. F inverse I. Now what is df? df A. So if you compute dfa of H, it now we see it's a matter of computation. So dfa H is HA transpose plus AH transpose. Okay? Okay? Now, for A in ON, dfa K of A is K plus K transpose. Now, given any S symmetric matrix, take K equal to S by 2. This implies df at the identity is surjective. So apply the above theorem to conclude that ON is a smooth manifold of dimension n plus 1 by dimension n square. So look at the above theorem. So this is a dimension of Mn. This is Mn. Okay. So we are defining a map from Mn to F. Okay. Mn means n by n matrices. Okay. So define a map from MnR to symmetric n by Fa equal to AA transpose. Now then your On is just the level set of identity. You compute the differential of F at any point, that is HA transpose equal to plus AH transpose, and for A belongs to On, d of A, Ka, where K is any matrix, okay, is K plus K transpose. Okay. So now take any symmetric matrix, take K as h by 2, then dFi is S by 2 plus S transpose by 2. So you know that symmetric matrix, all symmetric matrices can be written as A plus A transpose by 2. So that's what we are using here. That's what we are using here. Okay. Okay. So this is dFi is subjective. Now because dFi is subjective, yeah, in the level set A belongs to F inverse C. So dF of I is subjective. So F inverse I, dFi is subjective. So F inverse of I should have the structure of an n-dimensional smooth manifold. So the dimension would be n square into n plus 1 by 2, which is n into n minus 1 by 2. So we are just applying this result here. So here, when we see d of fa of H equal to H transpose plus AH transpose, okay, you just you can write it the same as dFA and just write H as KA. Okay, KA is a new variable, so that you can do, and this will be equal to A transpose K transpose plus K A. Yes. dF of Ka, no, so already we are doing that. dF of Ka is K plus K transpose. Yeah, so you take S in symmetric n, then dFA is subjective for each A in On. And now you apply the above theorem to conclude that this is a smooth manifold. So this is how you can construct many smooth manifold. So similarly, you can also show that So similarly, OPQ is also a smooth manifold, and so on. Okay, so this was a kind of nice application of this result. Okay, so now whenever you have a smooth manifold, you can also define map between smooth manifold. So a map F M to N between two smooth manifold is smooth if for each x in M and the chart U alpha phi alpha with x in U alpha and chart maybe V alpha Vi psi I of n with f of x belongs to Vi, the composition map psi I compose f compose phi alpha inverse f inverse Vi intersection U alpha to wherever a filbert so this is smooth. Okay, is smooth. Phi alpha on F inverse Vi intersection U alpha is smooth. And definition, formal definition, a diffeomorphism F between two smooth manifolds is a smooth map with a smooth inverse. Okay, so there are examples of, you can construct example of smooth maps, and one can define tangent spaces to every point of a smooth manifold similar as before. I think I will stop here because we are already over 30 minutes. So I will stop here and I will resume in the next class.